Good afternoon, everyone. Now I want to do a quick snap poll. So that music, when you hear it, does it trigger joy or does it trigger trauma? So joy, trauma. So I see two trauma, and mostly joy. Okay, so I think we're doing okay. I don't have to change the music theme right before the exam. Anyway, where we left off at the end of yesterday is we'd been talking about priority queues. And we were thinking of what is a way to build a data structure such that we can very efficiently remove the largest item from it, or in some case we might build a data structure that's reversed, where we can very efficiently remove the smallest item from it. No matter how many times we add or remove things, the add and remove operations are going to be fast, as well as the remove from the front operation is going to be fast. Now the idea here is that we're not going to care about the arrangement of all the items in the middle all the time. The goal here is really to have these three operations performed very efficiently. And our use case for this would be something like distributing Taylor Swift tickets on the basis of grades. Now, I'm not sure how many of you were on the Swifties' Instagram and Facebook last night, but there was some very big drama around the revival of the Eras Tour in Paris. So if that's your thing, go online, take a look. I can promise you it's a world of pain for the songs that were removed, as well as some of the very exciting songs that were added. Come talk to me after class. So this led to our discussion of priority queues. We had our three operations, is empty, insert, and remove. Is empty is just a convenience one so that we know, like, is there actually a data structure there? And we talked about three different ways that we could possibly implement it, and we ended up settling on this one that we hadn't really discussed in detail yet, where I promised that we could get better algorithmic efficiency on all the operations we cared about, and this was a heap. It's another abstract data structure, which, who can remind me what that means? What's an abstract data structure? In your own words. Pranav.
Basically, which is not an inbuilt type of data structure that we need to add within here.
So Pranav says it's not an inbuilt data type, but there's something else about it in the fact that it's abstract. What this means is it's a data structure that we can implement using different kinds of underlying types. So we might implement it using a linked list, we might implement it using an array. There are all different ways that we could choose to implement a given abstract data type that ultimately is going to determine the algorithmic efficiency of the operations that we build using it. So what is a heap? Abstractly, let's start with the high-level representation, and then we'll turn to a concrete way to implement it using arrays. So a heap is pretty similar to a binary search tree. It's a type of binary tree, only it has a different core property. In the case of a heap, our property is a little more relaxed. We're just going to require that the parent is larger than all descendants. You could also reverse this for a different type of heap where the parent would be smaller than all the descendants. But for now, let's focus on the one where the parent is the larger element. And the goal here is to be able to remove the smallest, either the largest or the smallest element very, very efficiently. Now, depending on which way you built it, whether you built it so the parent is larger or the parent is smaller, that's going to determine whether it's find max that's efficient or find min that's efficient. And we're just going to call that remove, because depending on whether we've built a max heap or a min heap, a heap that's very good at finding the maximum element, or a heap that's very good at finding the minimum element, that's going to determine what our remove function does, whether it removes the largest or whether it removes the smallest element. So for a max heap, our rule is going to be that the parent is larger than all the descendants. And for a min heap, it's going to be the opposite. The parent is smaller than all the descendants. And again, this will be tied to the functionality of what the remove function actually does. Now, we're going to focus on the max heap, but let's compare it to binary search trees for a second, because they do seem pretty similar. So just as a reminder of what we did last time, a binary search tree had this stricter ordering. It's where the right child was greater than the parent, was greater than the left child. So there was a relationship between all three of these elements. So the parent had a relationship to the right child, but the right child also had a relationship to the left child. We knew that the right child was going to be greater than the left child. This is not the case for heaps. For heaps, we don't actually know the ordering of the children. We just know that the parent is larger than both of them. Another useful thing to realize about a heap is that every path in a heap, every time you follow a path going from the top down, it's going to result in a sorted list. This is fairly easy to see. So if the rule is that the parent is always larger than the child, then you're going to go from something big to something small. And if you go from that node to one of its children, then that new child that you've just reached should be even smaller, and so on and so forth. So if you're going from very big to less big to smaller, then you're going to have an ordered list as you traverse. So here is an example of our structure where we have, let's just take a quick look at it. We can see that 10 is smaller than 13 and 14. 13 is smaller than 15 and 16. 15 is smaller than 25 and 30. But you can see that overall we have this structure where the property holds throughout the whole thing. Now here I've actually shown you a min heap, but a max heap is the same kind of thing, just in the reverse order. So let's think about this in terms of the strictness of the properties that we're requiring for our data structures. So a binary tree is a tree where every node has a maximum of 2 children, between 0 and 2 children. So that's not a very strict requirement, but it still is a requirement. Then we can have the heap property, which says that the parent is larger than the children. And then if we want to get even stricter, we can have the binary search tree property. And what this is trying to illustrate is not just the different structures of different rules, which is kind of obvious. The idea is to say that by requiring different levels of strictness in your properties that must hold, you can actually get different algorithmic properties. So one of the things you're trying to do as an algorithmic designer is try and figure out, okay, what is the right set of requirements in order to get a more efficient data structure for my particular use case? It's not the case that the stricter you make something, the better it'll be. Sometimes it is the data structure that has fewer requirements on its properties that is going to be faster for the operations that you need. And other times it's going to actually require you to impose more constraints in order to get certain efficiency speedups. So again, the point of having heaps in our case was to make really efficient both the insertion, the deletion, but also removing the root. Because we're not going to care about removing the other elements, because all we want to do is find the maximum repeatedly. So one way to represent this is to use arrays. Now, you could do this other ways, but for today, we're going to focus on a concrete implementation of a heap using arrays, and that is also quite simple and gives us very good runtime, very good complexity problems. So here is a snippet from the textbook that provides a description of how you can actually arrange this in an array very efficiently. So given a certain node in the tree, let's say we start with the root. The 2 children of this node, so say we start with the root in location 0. The 2 children are going to be in the array at position 2 times 0 plus 1 and 2 times 0 plus 2. So that's locations 1 and 2. Now, if we want to find the children of the node in position 1, which is the left child of the root, then we would see that at 2 times 1 plus 1 and 2 times 1 plus 2. So that would be in locations 3 and 4. And you can easily do this calculation for any node in the structure to figure out where in the array it would be, allowing you to very efficiently traverse from a parent to its children without having to use pointers. You can do this O of 1 calculation to figure out where the next node in your data structure is. Now, if you want to do the reverse, you can do the calculation quite simply. It's just take the current position of the node you're looking at. Let's say that's I minus 1, that whole thing divided by 2, and that will take you back to the parent of that individual node. And the last thing to note is just that this tree is going to be automatically balanced, which means you don't have far more nodes on one side than the other, it's filling out kind of evenly. So a stick is impossible within this kind of structure. So this is because we can see this is inherent through the array positions because of the way we're filling up the array. And we don't need any extra space for the pointers. We literally just store the values we want in the array. So that's very effective. So the 2 operations that we're going to be doing for our insertion and deletion, and these are kind of key, are called sift up and sift down. The idea being, if we put a node at the bottom of the tree, How can we figure out its correct location? By moving it back upwards through the structure, or the reverse. If we have a node that we've just placed at the root of the tree, how can we find its correct location? By moving down in the tree. So let's start with insertion, which is done through the sift up algorithm. Now the core intuition here is check if the element you want to insert is larger than that element's parent. If it is larger than that element's parent, swap it upwards, and then just rinse and repeat. So let's take a concrete look at this in a moment, but the basic code here, the basic idea here is start with the index that you're looking at just at the position of the node. From there, check if the node's parent is smaller. If the node's parent is smaller, really you should be the parent. And so swap the parent down to where you previously were. So let's say we want to insert the value 29 into this heap. So the first thing to do is to attach 29 to the very end of the heap in the correct position. So I've just got these dot, dot, dots here, assuming that that whole right side of the tree is filled out, but we're not looking at it because it'd take more space to draw. So I'm going to first insert 29 over here. And in this case, we are looking at a min heap, and so we want to ensure that the smaller values are higher up in the tree. So this over here is actually a violation. 29 is smaller than 50. So let's start our sift up algorithm. 29 is smaller than 50, so what do? We swap. So let me do that. You'll have to excuse my handwriting. Okay, are we done? Where's there a violation? We have 29 is still smaller than 30, so we need to do another swap. Okay. So let's do our check again. Is the child smaller than the parent? No, we're in the right place now, and so if we look at the new structure, we have 10, then 29. 29 is smaller than both 40 and 30, and then we know that by virtue of the fact that 30 was always smaller than 50, the way we had it before, we're done. So we don't need to do any more changes. So taking our, oh, that's the wrong thing. So we can see that this operation, even though the code is starting to look a little more algorithmic, in terms of its function, it's fairly intuitive. You just take the node at the end, and then you check, is it in the right place with respect to its parent? If it's in the wrong place with respect to its parent, keep swapping up. So every time that you want to add a node to the heap, you can do this fairly simple operation. Yeah?
Is there an important way to follow? Like, could you get it different? Like, for example, when you did on the other side, if you put it.
Yeah, so let's imagine, how can I reverse this all the way? So let's say that I put 29 over here. Now this is wrong. Do not do this when you're doing a heap. Oh, what have I? Oh, there we go. Thank you. So don't do this. This is wrong. But let's say that I try to insert 29 by putting it there instead of putting it at the natural next position. So we'd put an item here, and then we'd put an item there, and then there'd be some stuff there and there. And in theory, we want to fill that out in a balanced fashion. Now, the reason why it's a bad idea to put 29 in this position down there is now you've violated that balancing property. So firstly, your algorithm isn't going to be as neat as what we had before. You'd have to write some weird extra code. But secondly, you've lost the benefit of having an evenly sized height at all locations. And so your algorithmic performance is going to be much worse, so we don't do that. So you put it at the next free leaf. So a complete tree, remember, is where all the leaves are filled out perfectly. So that would be, there's a node there, and then that node would have 2 children, and then that would have 2 children, and that would have 2 children. So that is a complete tree where the whole thing is filled out. And you want to say, like, for example, if one of these is missing, like say that one's missing, then the next free spot is there. and that will ensure that your tree is as balanced as possible, or in some cases you'll even get a complete tree. Make sense? Okay, let me just rewind this to where it was before for next year. Okay, what about deletion? Well, the way deletion is going to work is we are always going to delete the root in the heap. Why? Because we know that the root is either going to be the largest element in a max heap or the smallest element in a min heap. So taking out that element is only going to take one step. But of course we're not done because we've just removed the root, and so we're going to need to somehow fix up the rest of the tree. So it's not quite as simple as just taking out the root. We're going to need a slightly cleverer algorithm, and this is what we're going to call the sift down algorithm. So the very first step in delete is to move the root and swap it with the very last node in the tree. Swap it with the very last leaf. Then, once you put the very last leaf in the root position, we know that it's going to be in the wrong place. We've definitely violated the heap property, so we need to fix up our heap. So you swap the very last leaf into the root position. You now take whatever the root is out, and so you reduce the size of your tree by 1, and then you fix up the heap by bubbling what is now in the root position back down through the tree into its correct position. So the algorithm looks slightly more complicated, but I promise you it really isn't that bad. So the first thing you want to do is you want to get the children of the root. Just like in the previous one with sift up, we had to get the parent. Here instead we're getting the children, both the left child, which is 2p plus 1, and then the right child, which is 2p plus 2. So get the child, and then check if the heap property is so get the child and make sure that you're still within the bounds of the data structure. If child is greater than n in this code, then n is the size of our heap, and so that means it doesn't actually have a child. That's how we check using an array, is just seeing if we've exceeded the array bounds. Okay, so if there is indeed a child, then what we're going to do is check which of the two children are larger, and then sift down into the correct position relative to the two children. So if that's what our first statement is doing over there, our first if statement is making sure that if there are two children, that we're going to swap ourselves into the position, the larger position of the two children for a max heap, or the smaller for a min heap. Now, it's a little wordy to just say that, so let's do an example on here. And I know I haven't switched to it yet. So at this point, we have a heap where our heap property is violated. 29 is violating the heap rule because we can see that it is not smaller than both of its children. That 15 is in fact smaller. So the first thing that we're going to do, we're going to go down and compare, is 29 smaller than its child 15? No, it's not. So we do a swap. Now, is 29 smaller than both of its children? No, so we're going to do a swap. And in this case, because it's a min heap, we're going to swap with the smaller child rather than the larger child. Oh. That was not what I wanted. $29. 20. And now 29 is in fact smaller than 30, so we are done. Now let's actually try do a full delete. So this was just an example of sift down. How would delete work? So what we do is we will swap out the 15 and the 30. So we will put 30 at the root because that is the last leaf. And now 15 is actually the one that we wanted to remove. So let's just reduce the size of our overall heap by 1, because the 15 was the item that we actually cared about getting. So now we've got 15, but our heap is now messed up. So we have to do this process again. So which is the smaller of the two children of 30? Well, that would be 20. So let's put 20 in there. 30 in there. Now 30 is not smaller than both of its children. It is, and the smaller of the two children is 25. So let's put 30 in there. And now 30 is smaller than both 35 and 37. So we're done there. Now, this is all well and good once we've already built a heap, but we actually want to be able to build the heap in the first place given a set of elements, because we often do start off with a set of elements that we then want to actually put into one of these data structures. So just like the other data structures we've done so far, we're going to do it via a process of repeated addition, or there are some tricks with a heap where you can actually build it faster than just naive repeated addition. So to build a heap, what you could do is you could just do the sift down operation over and over. So start with the root, put the root there, it doesn't have any children, you're automatically done. Now you add another element. Can you put that element at the root and then keep doing sift down again and again and again. Now, the whole goal of this in the end was to build a priority queue, but it turns out we can also build a highly efficient sorting algorithm using a heap. And this is called Heapsort, and this is the entire code for Heapsort. So just like with Quicksort, if you already have these functions, have the auxiliary functions like partition, the code for the sorting algorithm itself is really simple. And remember, the reason why this works is because of this property where any traversal through the tree is going to give you a sorted list. And so if we do in order traversal, then what we're going to get is the complete sorted values of the entire array. So the way it works, you build the heap, then you repeatedly swap the elements so that you have done sift down for every element in the heap at least once. And you know that if you've done that, then you must have a complete sorting across the entire heap. So let's evaluate the worst case runtime for some of our operations. So let's first look at so now let's start by analyzing the runtime of Heapsort and see just how good we've gotten. So remember, to do Heapsort, we had to do build a heap, and then n times we had to do this swap, and n times swaps is just going to be n, and then we have to do sift down. So we have to figure out the complexity of sift down and sift up as well. So what's the worst case runtime of Heapsort? So how many times do we call sift down? Well, we're calling it n onto -1. Let's start with sift down. So with sift down, how many times could I possibly need to sift something down further and further down? Well, we know that given we've got a balanced tree, so wherever we sift down is going to be the same amount. And that's always going to be h, the height of the tree. That's always going to result in a maximum of h steps because there are only h possible layers we can go down and do a swap. Then for our build heap, that's going to run in O of n times because we're adding n elements in and sifting down, but at each point we haven't yet filled out that layer yet. And so if we figure out on average how far down are we going to have to go, well, the first element is just going to be added to layer 1, and the last element is going to be added to layer h. If we figure out how many layers could we possibly have to go down. So let the bottom of the heap be level 0, and let's say we have n nodes total. If we would calculate how many nodes are at the very, very bottom of our tree, that's going to be a maximum of 2 to the h nodes. That's just by like the first layer has 1 node, the second layer has 2, etc., etc. So n is at least 2 to the h. So we can bound n. So n is somewhere between 2 to the h and 2 to the h plus 1 minus 1. And we know this just because of how many nodes there are on the very last layer. So let's do a little bit of math crunching. We know that there are a maximum of 2 to the h minus 1 nodes at the ith level. And we know that there are a maximum of I swaps for each node, because if we're at the ith level, you can only have gone down that many swaps to that level. So that tells us for a given entry for a given node in our heap, how many swaps will it have done? So we do some crunching, we use our bounds, and we know that n is at least 2 to the h, so we can substitute that in, and we end up with this equation. So the overall running time is bounded by 2n, and therefore the overall runtime of our construction is just O of n. And that is perhaps a little surprising result that we get from using sift down instead of sift up in this case. Now we return to our Heapsort runtime. We saw that we could do build heap in O of n, and we know that we only have to do a maximum of n calls to this second part, and sift down itself will take log n time, which is the height of our tree. And so what do we get overall? We get build heap takes O of n, remove max takes log n, because that is how long an individual call to sift down will take. And then to remove n maxes, that's going to take n log n. And that's our entire heap sort algorithm. So we have O of n for the building heap, log n every time we want to do a sift down and remove the max. And given that we're doing that once for every element in our array, we get a worst case runtime of O of n log n. Now, how does this compare to the previous algorithms that we've seen before? Does anyone remember what was the best that we had previously? What was that, Pranav?
For sorting?
Yeah, for sorting. Was that average case or worst case? Yeah, that was average case. So quicksort gave us average case n log n, but Heapsort gives us worst case n log n. So we've actually made a substantial improvement. But I forget who it was that came up to me. Someone asked, so do we use Heapsort all the time? And the answer is no. We actually commonly use a combination of quicksort and one last sorting algorithm that we will talk about probably next week. And what's the reason for this? Well, even if theoretically there are this many operations that we have to do in the worst case, firstly, it's a worst case. It actually doesn't correspond to what will happen on real-world data and real-world distributions. And on top of that, the number of operations may be bounded by n log n, but every operation in a computer might actually take subtly different amounts of time depending on the particular operation you're doing. So swapping something might not take the same amount of time depending on where you're swapping something to and the particular data structure you're using. So as a result, in the real world, we use sorting algorithms that typically combine quicksort for certain structures of arrays with merge sort for other arrays. And we'll talk more about merge sort next week. Yeah, Sebastian.
Is that it, like for sorting, is this the best you can do? Like worst case and log n?
As far as we know, I actually think it's provable that n log n worst case time is the best you can do for sorting. However, what it actually looks like on a realistic piece of data is going to, on a realistic distribution of data is going to differ. And the other thing is this is for totally generic sort. So for example, if you know that all of your numbers are going to be between 0 and 100, you can do better than that. So this is the best case generic sorting algorithm. So let's take a look at heapsort.c. So here we have heapsort.c, and we're going to include sort scaffold, which is just some scaffolding code that you might have seen earlier in semester that enables us to actually test our sorting algorithms. So the two important things that are going to be in sort scaffold, just for your awareness so you don't get confused, we have a comparison function that's defined, as well as a swap data function that's defined that'll swap the data in two different nodes. So we have our three functions, build heap, sift down, and heap sort. And sift down is what we said before. Get the child and set it. Figure out if the child is smaller than the size of the original, than the size of the heap. So is there actually a child there in the first place? If there is a child, check if it is larger or smaller. If the right child is larger than the left child, then move to the right child, because that's where we're going to want to put our new element. Then if the parent is smaller than the larger two of the children, swap it in and then just sift down. And that's the whole function. For build heap, it's exactly what we saw before. For every element, take the element and sift it down. And then heap sort, again, pretty simple. Build the heap, and then just do the sift down with the swaps repeatedly. And that's it. That's the whole code for heap sort. So let's compile it. So I'm just going to go ahead and compile my Heapsort demo and run it. It runs well on uniform items, but doesn't exhibit a meaningful speedup on sorted or reverse sorted. So I'm just going to go ahead and compile my Heapsort demo and run it. It runs well on uniform items, but doesn't exhibit a meaningful speedup on sorted or reverse sorted items, as opposed to random. Now we'll do the same for quicksort. So you'll see quicksort has the same sort of pattern, but with fewer comparisons and a few more copies in this particular implementation. Now in practice, you can get quicksort to make fewer copies than heapsort, and also take advantage of the fact that quicksort does most of its work on memory locations that are close to each other, and that ends up making quicksort faster in many cases, thanks to the way that CPUs are designed. And so what this gives us is sorting in worst case of n log n, which is a big achievement for our class. We've been building up to this for a long time, so pretty happy. But now we're going to come into questions of how do we deal with things when our data is not small, which is not just a couple of integers, but it's actually really big. So I'm going to take a few suggestions from the audience about what to do when our data set is really large. Does anyone know how much memory their laptop has? Okay, let's see if I can read that. That's 8 what?
Gigabytes.
8, I see a G, and 8G, what's next? B, 8 GB, okay, 8 gigabytes of memory. Okay, maybe we can keep this communication up. So if I've got okay, we'll take another bite and we'll keep going. So if we have a very large amount of data that exceeds 8 gigabytes, what are our options for continuing to sort it? I hope you're getting this, Rithik. Okay, we take it and we put it. I'm going to need some better charades here. Okay, you take some of it, and then what do I do with that sum of it? Oh, and then I put it back together. So you're saying I should split it up? No? No? That's okay. You still, that was a good idea. But I liked where your mind was going. So it was like here and here and here and here. Do you want to tell me what you were thinking?
Why don't you go iteratively through the heap?
So take the microphone. Or unless you want to take another bite. Okay, so the suggestion was to go iteratively through the heap, and that would be okay, only we can't fit the heap in our computer's memory. So does anyone want to finish off the thought for us? What can we do? Our computer has only 8 gigabyte of RAM.
Can you sort the heap in like subheaps?
Okay, subheaps, we're starting to get better ideas. Sharon, did you have an idea? You want me to pass you the microphone? I like this charades though. We should do this more often.
Maybe store some of the data set somewhere outside of RAM.
And where? What do we have that's not RAM?
Secondary storage, like text files.
Like a text file. That is exactly where we're heading. So what we want to do is we want to store our data somewhere that is perhaps a bit slower than RAM, which means our sort is going to be slower. But we're actually going to have enough space for our entire data set. Now, what is the really big downside of doing this? What was your name?
Nancy.
Nancy.
Yeah.
What is the downside of doing this? Like splitting it up into text files and then starting to do it that way?
You have to access the files every time you want to like sort or insert or delete.
Yeah, and do you have just a vague sense of how the speed of the hard drive compares to the RAM?
RAM is much faster.
Much faster? How much faster? Like, give me, is it like 10% faster? Is it?
I don't know. I'll guess like a lot faster.
A lot faster. So we're talking like 1 to 2 orders of magnitude faster, depending on exactly the speed of the particular type of hard drive you're using. So we're talking about a whole order of magnitude slowdown when we're trying to sort things that are larger than our computer's memory. So I might, if we get a couple minutes at the end, talk about how we can get around that, but for now, let's just try using the file approach. Now, the other problem is that heaps are not very well designed for splitting up into little pieces. It's not clear exactly how you're going to split it up, because the way that you're jumping from parent to child is by going like 2 times the index plus 1, which means if you have a very large heap, the bit that you're going to be looking for might be in a different file, so you can't even read just that file into RAM. So we're going to need some better kind of algorithm that works well for doing this sort of thing. So the strategy we're going to use at this point is something called divide and conquer. And this is beginning to take us towards the end of the class, where we're talking about different strategies that we can use to come up with algorithms. The basic idea here is going to be to split up the work at least for, let's say we have a 16 gigabyte-ish heap. Let's split it into 2 halves, an 8 gigabyte half that'll fit in our memory and at one time, and then we'll sort that, and then an 8 gigabyte half that we'll sort later and bring that into our memory, and then come up with a way to combine them that does not require having them both entirely in memory at the same time. Now, of course, I'm fudging a little, because if you have exactly 8 gigabyte worth of items, then you're not going to have any memory left for temporary storage or for your operating system or anything. So we have to figure out where we're putting the chunks. And so we're going to put our chunks either on our spinning hard drive or on an SSD. I just bought a new one of these, 2 terabytes. It's about that big, for $150 this week. Unfortunately, I also wiped my entire hard drive in the process of installing it, which is why I am not as well rested today. So how do we actually practically go about doing this in C? Well, we have a few functions that we'll use to open files, to close files, to read them, and to write them. And finally, you're not going to have to keep relying on using standard input and output in order to get data in and out of your program. So the Unix philosophy around this is also pretty interesting, because everything is a file. You can access the entire system's memory as if it was a file as well. There's a file on a Linux computer called /dev/mem, that's location. And if you were to open that and start reading it, you'd be reading the RAM from the computer. Likewise, if you read from /dev/cd-rom, you'd be reading what was in the CD-ROM drive. So everything in Unix is treated like a file, which makes it very powerful, because you can change settings just by writing something to a file, or you can change what a light is doing on the computer. If you have like a little LED, you can make the LED flash by writing to a file. You can see if the LED is on or not by reading from a file, etc., etc. Very, very powerful. However, there are 2 kinds of files. There are binary files that represent things like memory and data, and then there are just ordinary ASCII text files, which you could open up. So just because I've told you that everything on Unix is a file doesn't mean that you can like open it up in your text editor and start playing around with it. There are different types of files, and the binary files aren't going to make much sense to you just reading them there. So all of these functions that we're going to use for our files are going to take a file star. Now this is a pointer to a file struct. And a file struct is one of these things defined in some header file that you're going to use. So you're going to use standard io.h, and that's going to have this code somewhere in it, along with there's a ... so there are a whole bunch of other things. And a few things that we're going to keep track of under the hood is it's going to keep track of where the file is on the computer, if it's already open or not, how far through the file you are up to reading it so that you know the next bit of the file to read, and then the actual buffer that you can read from in order to read the next chunk or so of that file. So our operations are going to be open the file, navigate to where in the file we want to read from, read that chunk, and then it will automatically move the buffer over up to the next chunk that we're able to read from. So if you call read from a file multiple times, you're going to be able to get chunks. Now, we also have seen a few files already, but they've been disguised. So standard in, standard out, and standard error have what's called file descriptor numbers associated with them. Now, every time you open a file, the operating system is going to keep track of how many open files you have, and we'll say like file 0 is this one, file 1 that's been opened is this, file 2 that's been opened is that. This is separate from the file pointers, which point to that struct, but the operating system is also keeping track of how many simultaneously open files there are. And 3 files that are always open every time you start your program are standard in, standard out, and standard error that you've already been using through printf and scanf. So there are these 2 other functions that are actually been operating behind the hood the whole time, fprintf and fscanf. And these are the same as printf and scanf, only they require you to additionally specify which file number you're printing from, or which open file number you're scanning from. And so what's happening behind the hood when you call printf is it's running fprintf, but just already putting in for you the fact that std out is already the number 1. And when you do fscanf, when you call scanf, it's really calling fscanf, just with the built-in number 0 to read from standard in. So when we open a file, we also have to set the mode in which we want to open it. So we have to tell the computer what we're planning on doing with it. Are we planning on writing to it? Are we planning on starting a new file? Or are we planning on reading from it? Now, there's a bit of a gotcha here. If you choose W, which is for write, it actually starts the file fresh. If you want to write to the end of the file, you've got to put in A, which is append. So be very, very careful, because it's easy to overwrite an entire file by accidentally using W instead of A. Now you can also add a plus at the end of this to enable 2 other functions that allow you to jump to different positions in the file and don't just require you to read sequentially. So let's actually write up an example of this on the computer. And I will call this file io.c. So let's create an int pointer, and we will call this int pointer. Now I'm going to create a pointer to the file that I'm going to open. Now, just creating the pointer, remember, if you haven't set it to null, if you haven't initialized it, it's just going to be some random value. So we will call this data file. And now let's set int pointer equals and let's make room for 10 integers. So what I've done is I've allocated room for 10 integers, and now I'm going to free it just at the end of the program. So I'm writing this in advance so that I don't forget it. Oh. So now I can call my fopen function. And the first argument to fopen is the file name. So in this case, I'm going to use // to refer to the current directory. And I'm going to just call this one data.txt. And then I will open it in write mode. So that code is legitimate, but what I've forgotten to do is I haven't actually set the outcome of this to any variable. So I've opened the file, but I haven't kept track of the structure that's been created as a result. So what I need to do is I need to actually store the outcome of that. Oops. Need to store the outcome of that in my file star, in my pointer to the structure that's going to keep track of that open file for me. Now, in good practice, before I forget, I'm just going to do fclose at the end. It's just like with pairing malloc and free, you should always pair an open with a close. Otherwise, you can run into problems where you think you've written to the file, but the operating system hasn't finalized that yet, and your program ends, and the operating system forgets about writing that data to the file. Okay. So now probably what we want to do is we do want to check if this succeeded. We know with opening and closing files, if the file doesn't exist, if the directory doesn't exist, we can run into all kinds of issues. So we do want to check if this actually succeeded. And so I will put this in an if statement. And if you were to look at the man page for fopen, you'd see that if it fails, it's going to return null, and otherwise it will return a valid pointer to the file structure. So this is if it is null, then I'm going to do fprintf. And now for the first time, I'm using fprintf, which allows me to specify to what file am I printing. And now I'm going to print to std error. This is very similar to standard out, where the only difference is this is specific for errors. And so it allows you to actually, if you wanted to, when you are running a program, see just the errors or see just the output. You could send the output to one place and send the errors to another place. And so this is just a kind of way to keep our streams of thought more easily separated. Okay, we're almost there. And now we want to do, actually, let's do a read in the time we've got left, because it's not very long. So let's do a read. And read, and we are going to read into there. So I've got it written down what the order of parameters is, but if you wanted to look it up, you could just go into the man pages. And so the order is the destination, what size each of the items that I'm reading in are, how many of them I'm reading in, and the location, the file pointer to where I'm reading them in from. So this will allow me to read it in, and I want to check that I have indeed read in n items. And if I haven't read in n items, then I'm going to do fprintf standard error, read error. And then I've done fclose data file and free the pointer. So now let's, in the last minutes of class, I'm going to compile this. Oh, there we go, and that succeeded. And now what I'm going to try and do is I'm going to create another file, 1, 2, 3, 4. And we're going to see this won't work, but I will explain why it won't work next class. Okay. So we have a mystery, and this is where we're going to lead off, and something for you to think about over the weekend is what is the problem? So it's kind of subtle. We've done almost everything right up to this point, but we have a bit of a mystery left over. And with that, thank you very much, and I will see you next week.